For the next reaction, we're going to do an addition reaction with a strong Bronsted acid with an alkyne this time. Now, I'm going to look at two versions here. I'm going to look at an example where the cation that's generated is going to be resonance stabilized, and it will proceed via a mechanism. And then there's going to be a situation where you can't generate a carbocation because there's no resonance to stabilize it. So we have to invoke a different mechanism. Now I'm going to show you the mechanisms of how these reactions occur, so we think. I'm going to keep it simple so it will help you learn the chemistry and learn how to predict products. But I want you to know that there's a lot of evidence out there that suggests a mixture of mechanisms. And depending on your professor and who you talk to, they may decide to have you learn a different mechanism of what they feel is better. So this mechanism isn't just clear cut. Right? There's going to be a lot of variations, but the version that I'm going to share will keep things simple enough so that you can be able to use the mechanism to predict products. Okay? So let's take ourselves a alkyne that looks like this. Okay. Please note that that phenyl group right there is going to represent a benzene ring, right? So this is an example of a resonance stabilized species. If we treat this with HCl, and we have to make sure that this isn't excess, okay? And we do this reaction, what's going to happen is we're going to generate a geminal dialkyl halide that looks like this. And what has happened here, if we number the carbons, carbon 1, carbon 2, so on carbon 1 we see that we've attached 2 chlorines, and then to carbon 2 we have attached, we already have a hydrogen there, but we have attached 2 more. So for a total of 3 hydrogens. Okay. So how does this happen? So the first thing is we have pi electrons once again, and those are going to be electron rich. So we're going to use that electron rich pi electrons there to abstract a proton. And so that's going to be the same step that we've seen before. That's our electrophilic addition step. And so that's going to happen. Pi rich, electron rich species attacking electron poor species is going to generate this. Now this, and so where did that hydrogen go? It went to carbon 2. So we already have one that was originally there, and now we've added the second one. So what did that generate for us? That generated a carbocation right there. And we call that a Weinlich carbocation. Okay? And Weinlich carbocations are not stable. They're not very stable at all. But the reason why this particular one is going to work for us is because we have the benzene ring. So if we expand out that phenyl right there to a benzene ring, do you see now how we could draw a resonance structure where those pi electrons can come and stabilize that Weinlich cation? Right. So there's our first step right there. This occurs because it's stabilized. But we will see situations where that does not, there is no stabilization, which we'll talk about after I go through this problem. And so now we have what we still have, we have the chloride now floating around. So we will do a coordination step. Do the coordination step. Take those electrons, attack right there to generate represented like that. And then we will do the same two steps all over again. We will do a electrophilic addition step, so I'll just go EA for that. Electrophilic addition step with another molecule of HCl. Same mechanism. The hydrogen's going to go to the carbon with the most hydrogens. Right here. And generate a stabilized carbocation. And then we will do our last step right here. And with what? We have another chloride floating around, which will then proceed to come in via a coordination step to generate our product. Okay. And so what did we generate? We generated a geminal dialkyl halide. And geminal simply means that the halogens that have been added are added to the same carbon. Okay. So next, let's take a look at the mechanism that we can invoke when we don't have the ability to stabilize a vinylic carbocation. So here's an example of an alkyne that doesn't have any groups attached to it, like a benzene ring, that can stabilize the vinylic cation. So let's try to do the mechanism the incorrect way first to show you what I'm talking about. So if we do our electrophilic addition step, we will generate something that looks like this. Like that. There's a vinylic carbocation. And there's nothing over here that can help to stabilize that vinylic cation. So this cannot happen, okay, because that is so unstable. So another mechanism is proposed, but because this reaction can still happen, and it does it very nicely and efficiently, it just doesn't proceed via the mechanism that I just previously showed you. So the mechanism that we can invoke, and I'm going to redraw this molecule down here just to have a little better approach to it, is where we're going to take two molecules. We're going to take our HBr. I'm going to draw it like this, just to orient it in that direction there. And then we're going to have another bromide. There's our other bromide right there. Okay? And so what's going to happen now is we're going to use three molecules in this mechanism all at the same time. So what happens is the electron-rich electrons here going to attack the electron-poor hydrogen in the same manner that we've seen before, like this, kicking that guy off. Okay? But here's the new part. We'll take this bromide right there, and it's going to attack this carbon right there. Okay? So it's kind of following the Markovnikov process here, where we're going to take this hydrogen and add it to the carbon that has the most hydrogens, which is carbon 2. And so that's going to give us this right here. Like this, Br. Okay. And now we just invoke the same mechanism that we've seen before. We will do our electrophilic addition with another equivalent of HBr, like this. Hydrogen will go to the carbon with the most hydrogens. We generate a carbocation. And then we will do our coordination step with the other bromide. So we have bromide floating around. And then that will come in to give us our product right there. So that is the mechanism. All right? I hope that helps everyone.